things have their cycle of life, of usefulness. So it is with an experimental reactor. And the end of an experiment means the dismantling of systems and structures so that new structures, new knowledge can rise from the old. But how do you dismantle a radioactive facility? How do you convert a nuclear site into a useful area for other operations, other life cycles? The decommissioning of the Atomics International Sodium Reactor Experiment, known as the SRE, helped provide answers to many of these questions. Answers that could be used in the safe dismantling of other surplus nuclear facilities all over the world. Atomics International was an early pioneer in the field of nuclear development. SRE, the sodium reactor experiment, was conceived in the late 1940s and went critical in 1957. It was designed, constructed, and operated by Atomics International, at that time a division of North American Aviation, under the auspices of the Atomic Energy Commission, to investigate the concept of a low-cost, high-performance sodium graphite reactor for the development of economical electric power. In those days, the SRE was radically different from other reactor concepts. It incorporated a 20 thermal megawatt reactor having many of the design features of a full-scale central station sodium graphite reactor. Liquid sodium served as the coolant and heat transfer medium. Reactor fuel was metallic uranium contained in clusters suspended within the core. Moderators made from graphite blocks clad in zirconium surrounded the fuel elements. During 27,000 hours of operation over a period of 7 years, the SRE provided extensive data on reactor performance, maintenance, and nuclear safety, while at the same time generating more than 37 million kilowatt hours of electric energy. Nuclear experiments were concluded in 1964, although the sodium systems were operated until 1967. At that time, the radioactive fuel elements and control rods were removed, the primary sodium drained, and the entire facility placed in a status of protective storage. In 1974, it was decided to decommission the facility and remove all significant reactor-originated radioactivity so that the site and the major structures could be used for other purposes. But the dismantling of the facility, much of which was contaminated, required unique approaches and equipment. No attempt would be made to salvage any equipment or material that could not easily be decontaminated. All contaminated material, components, and structures would be transported to a commercial nuclear waste disposal site in Beatty, Nevada, and buried. The major problem involved removal of the reactor vessel and its sodium pipe connections. The reactor core tank was 19 feet deep and 11 feet in diameter. It was located beneath ground level. The core tank was concentric, with a thermal shield, an outer tank, thermal insulation, a steel vault liner, and a concrete radiation shield. Stainless steel thermal bellows sealed the top of the core tank and the outer tank. The building interior was shielded from radiation by a 6-foot thick plug. In order to develop techniques and tooling for disassembling the reactor vessel, a mock-up was constructed. 16 feet in diameter, the mock-up simulated the largest diameter of the reactor vessels. Cutting up the stainless steel elements of the vessel and other components would require a plasma arc torch operating remotely underwater. For this reason, a remotely operated, rotating mass torch manipulator was developed and installed in the vessel mock-up. The manipulator, designated the Mark I, was based upon an existing design of the Oak Ridge National Laboratory. An existing manipulator control console was obtained from Oak Ridge and modified to give it the required versatility. Initially, the torch was operated in air to develop cutting parameters. Subsequently, the tank was filled with 12 feet of water and the parameters refined. Video cameras were used to position the torch at the beginning of a cut, but could not be used during the operation due to the intense light. A plasma arc torch operates in an inert atmosphere and develops a temperature of approximately 80,000 degrees Fahrenheit, allowing it to easily cut through 6 inches of stainless steel. Rate of cut on 1/4 inch stainless was between 3 and 4 feet per minute. The first cuts were made along the walls of the tank in sections approximately 3 feet square. Cut pieces were studied and refinements made in the cutting process. In order to cut the rounded bottom of the reactor vessel, it was necessary to develop a special arm for the manipulator so that it could cut a radius. This configuration was termed the Mark II. After dry checkout, the Mark II was tested underwater in the mock-up vessel. While plasma arcs perform extremely well underwater, their performance must be carefully controlled. The cut must begin at a slow rate, produce a rapid cut, then end at a slow rate. If the arc is lost, it is necessary to start a new cut, since it is impossible to cut through the solidified metal of a previous cut. Operations in the mock-up vessel allowed the development of optimum rates of cut, gas flows, and water purge systems, as well as the development of cutting techniques and procedures. These are sections cut from the mock-up that range in thickness from 1/4 inch to 1.5 inch thick stainless steel. It was also necessary to develop special remote handling tools to grapple and remove the cut segments from the vessel. While many were constructed by modifying commercial equipment, most had to be specially designed for the task. Grappling, in most instances, had to be performed prior to cutting to prevent the cut segment from falling to the bottom of the tank where retrieval would be difficult. It was also necessary to develop special pry bars and wedges. This one, for instance, was designed for use on bands that surround the vessel. Since a plasma arc torch cannot cut through plates that touch one another, a spacer was developed to support the core tank bottom after it had been lifted away from the outer tank bottom. A plasma torch also cannot cut past a hole, so it was necessary to manufacture 1.5 inch thick plugs for the more than 100 coolant flow holes in the grid plate. It was also necessary to develop tools and techniques for the use of a standard oxygen-acetylene cutting torch, since a plasma arc does not perform as well as oxyacetylene when cutting carbon steel. For example, work on the mock-up determined that it would be better to lift each carbon steel thermal ring out of the reactor pit and cut it up on the reactor room floor rather than cutting each of them in place. Cutting the stainless steel internal plumbing presented special problems. Use of the plasma torch or conventional cutters was impossible, since the plumbing ranged in size from 2 inches to 12 inches in diameter and included pipes within pipes and elbows within elbows. The decision was made to use explosive cutting. Consequently, experts were contracted who had extensive experience in the explosive cutting of large diameter pipes in oil fields. Underwater tests were made using special explosives and shaped charges which produced implosions rather than explosions. These are samples of stainless steel plumbing cut with shaped charges. While the cutting development tests were taking place, disassembly was begun of the non-radioactive sodium equipment support structures and cooling systems. This work was accomplished by a salvage contractor. During these and all other operations, Health, Safety, and Radiation Services Department personnel surveyed all equipment and materials removed for radioactive contamination. In preparation for disassembly of the reactor vessel, all residual sodium was drained from the vessel. Primary sodium, which had been stored in the fill tank, was drained into 55-gallon drums. This sodium was slightly contaminated and was later shipped for use in DOE facilities at Hanford. With the sodium drained, the system piping was cut into manageable lengths using hydraulically powered rotary cutters and portable bandsaws. After cutting, the pipes were capped to preclude air entrance and a reaction with residual sodium, as well as to prevent the possibility of contamination release. The pipes were then lifted from the vaults by crane. The cleared concrete vaults were cleaned so that later they could be fitted with storage tanks to hold the radioactive sections as they were cut from the reactor vessel. Two of these storage tanks, made from quarter-inch steel plate, were installed in the cleared vault. On the hillside above the SRE, the radioactive liquid waste holdup tanks were excavated. These tanks were shipped to Beatty, Nevada for burial. radioactive gas decay tank concrete vaults were decontaminated and broken up. Small areas of the surrounding concrete and soil were found to be slightly contaminated. These were removed and the contaminated material packaged and shipped for burial. The area was backfilled with uncontaminated concrete rubble and soil, then graded, making the site acceptable for any subsequent use. Inside the building, the 3 fuel and moderator handling machines were removed from their parked positions and placed horizontal. The machines were approximately 30 feet long and weighed from 25 to 60 tons. Their internal surfaces were highly contaminated. Salvageable external components were removed and the machines shipped for burial. Dismantling of the reactor vessel began with removal of the shield plug. The facility handling fixture was used for the operation, which involved rotating and lifting the 56-ton structure. Radioactivity of the shield plug was fixed by painting it, then covering it with plastic to protect the surface. The graphite moderator elements were then removed. These had never been subjected to reactor operation and therefore had no neutron-induced radioactivity and were only slightly contaminated by sodium contact. For shipment, they were placed in plastic bags to contain loose radioactivity. Cutting of the stainless steel bellows presented unique problems. It was necessary to develop a special auxiliary manipulator for a small plasma arc torch, which revolved around the inside of the vessel. Cutting of the bellows freed the ring shield, which provided support for the shield plug. The ring shield, which weighed 60 tons with 3-foot thick walls, was also wrapped in plastic for containment of low-level radioactive particulates. Special trucking rigs were used to haul both the ring shield and the shield plug intact to Nevada for burial. With the reactor vessel now opened and filled with shielding water, the Mark I manipulator and its control console were removed from the mock-up and installed for use on the reactor vessel. Using the video camera, a survey was made of the vessel interior. The survey showed that there were a few discrepancies from the engineering drawings, but that the tooling and techniques developed in the simulator could be applied with little modification. The first task was cutting the internal plumbing with explosive shape charges. The charges were set in place by means of a spring-loaded clamp that inserted the charge around the pipe to be cut. As anticipated, the implosions produced only minor disturbance of the water, even though the charges were heavy enough to easily sever a 10-inch diameter pipe with half-inch thick walls. A critical operation was cutting the concentric reactor vessels. The cutting operation proceeded without incident, using the procedures and techniques developed during the year of preparation on the mock-up vessel. As each cut section was brought up by the grappling and handling tools, it was washed with clean water prior to removal from the vessel to minimize the transfer of contamination. After removal from the vessel, the segments were placed in a special cask liner made of half-inch steel. When a cask was loaded with a liner containing about 6,000 pounds of material, it was capped and placed inside one of the water-filled steel-lined storage vaults. Holes in the bottom of the cask liner allowed water to enter and exit. When ready for shipment, the casks were taken from the storage vaults and placed in lead-shielded shipping casks. In preparation for removing the grid plate at the bottom of the vessel, a video camera survey was made. Each of the holes in the grid plate was plugged before the plate was cut into segments with a plasma torch. By the end of summer 1978, most of the operation had been completed. The only tasks remaining were removal of the insulation and the concrete biological liner. When these are complete, all remaining contaminated concrete and earth will be removed and shipped for burial. The building structure and the surrounding area will then be available for unrestricted industrial use, having no more radiation than that naturally found in the surrounding California terrain. Thus ends the SRE, sodium reactor experiment, leaving a legacy of knowledge that today is the leading edge in man's quest for energy. Energy without end.